Hello, my dear students. I am going to start the remaining portion of relation for class 11. So, one problem, suppose if A equal to 1, 2, 3, 4, 6. 1, 2, 3, 4, 6. Then, at the very beginning, we have to find A cross A. Then, here we have given R is a relation such that R is a relation such that x comma y such that x comma y such that y is exactly divisible by x. Y is exactly divisible by y is exactly divisible by x. Y is exactly divisible by x where x comma y belongs to A. X comma y belongs to A. Then what will be the relation? First of all, 1 1, 2 2, 3 3, 4 4, 6 6. So in each case, y is exactly divisible by x. Again, 1 comma 2, 1 3, 1 3, 1 4, 1 6, then 2 4, 2 comma 4, and 3 comma 6. 3 comma 6. So here in this case, second one is y, first one is x. So y is exactly divisible by x. Y is exactly divisible by x because 1 is divisible by 1 itself, 2 is divisible by 2 itself, 3 divisible by 3 itself, 4 is divisible by 4 itself, and 6 divisible by 6 itself. Again for 1 comma 2, 2 is divisible by 1, 3 is divisible by 1, 4 is divisible by 1, and 6 is divisible by 1. Again here 4 divisible by 2, 6 divisible by 3. So total number of elements will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So total number of elements will be here 10. In this relation, whenever y is exactly divisible by x, then in this case we can say these are the relations from A to A. How many elements are there in and list them? Already we have written find R inverse. So R inverse can find as reciprocal of inverse order pair means 1 1, 2 comma 2, 3 comma 3, 4 comma 4, 6 comma 6, then 2 comma 1, 3 comma 1, 4 comma 1, 6 comma 1, 4 comma 2, and 6 comma 3. inverse also same. There will be 11. Find R inverse. Then domain of R. The domain of R will be D of R. D of R will be domain of R. A itself 1, 2, 3, 4, 6. 1, 2, 3, 4, 6. Then range of R 1, 2, 3, 4, 6. Again range smaller or capital R. Range of R A only. Then domain of R inverse. Domain of R inverse. So domain of R inverse 1, 1, 2, 3, 4, 6. Again it is A. Then range 1, 2, 3, 4, 6. Again A. R inverse also A. 2, 6. So one more order pair is supposed to be here. It will be 2, 6. So if A equal to 1, 2, 3, 4, 6, then R will be equal to 1, 1, 2, 2, 3, 3, 4, 4, 6, 6, 1, 2, 1, 3, 1, 4, 1, 6, 2, 4, 2, 6, 3, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There will be 12 elements. There will be 12 elements in relation R. So similarly in the case of R inverse also there will be 12 elements. And here domain of R, range of R. Again domain of R inverse, range of R inverse, all will be A. It will be same. So let us see the next question. Let A equal to, next question, let A equal to 10, 11, 12, 13. 12, 13. And B equal to 1, 2, 3, 4. 1, 2, 3, 4. B equal to 1, 2, 3, 4. Write the following relations from A to B as defined in each case. So, number 1 है R1. Within first bracket A comma B, such that A minus B is odd. For A minus B is odd for A belongs to capital A and B belongs to capital B. Then R will be A minus B should be odd. 1 minus 1. So then it will be 10, 1. Their difference will be odd. 10 comma 2 no, 10 comma 3, 10 comma 3, their difference is odd. 10 1, 10 3, then 10 4 no need, then 11 1 no need, 11 2, 11 comma 2, 11 comma 2, 11 comma 3 no need, 11 comma 4, yes, 11 comma 4, then 12, 12 comma 1, 12 comma 1, then 12 plus 2 no need, 12 comma 3, 12 comma 3, 12 comma 4 no need, then 13 1 no need, 13 comma 2, 13 comma 3 no need, 13 comma 4. That's it. So if we want to find a relation A comma B such that A minus B is odd for small a belongs to capital A and small b belongs to capital B, then under this definition of the relation, the order pair will be like this: 1 10 1, 10 3, 11 12, 11 2, 11 4, 12 1, 12 3, then 13 2, 13 4, because their difference is odd. 10 minus 1 is 9, 9 is odd. 10 minus 3 is 7, 7 is odd. 11 minus 2, 9, it is odd. Then 11 minus 4, 7 is odd. 12 minus 1, 11 equal to odd. 12 minus 3, 9 is which is odd. 13 minus 2, 11 which is odd. Then 13 minus 4 equal to 7 which is odd. So all these order pairs satisfy this relation. Therefore R1 in the order pair set it will be this one. From relation will be from A to B. Then next number is to say it is given as within first bracket A comma B such that A plus B is a multiple of 4. A plus B is a multiple multiple of 4. A plus B is a multiple of 4 for small a belongs to capital A and small b belongs to capital B. Then what are the order pairs for the second relation, that is R2? According to the definition, it must be A plus B should be multiple of 4. Means the summation must be divisible by 4. Then what are the order pairs? Let us see. Say 10 plus 2, that is 10 comma 2. 10 plus 2 equal to 12 is divisible by 4. 10 plus 13 no need. 10 plus 3 no need. 10 plus 4 no need. Then 11 plus 1. 11 comma 1. Then 11 plus 2 no need. 11 plus 3 no need. 11 plus 4 is 15. 11 plus 4 is 15. 15 also not divisible by 4. No need. Then 12 1 no need. 12 comma 2 no need. 12 3 no need. 12 comma 4 16 is divisible by 4. So 12 comma 4. Then 13 plus 14. 13 plus 2 13 comma 3. 13 comma 3, their summation is 16. So 16 is divisible by 4. So first, this order pairs, their summation is 12. 12. here it is 16, here it is 16. So 12 is divisible by 4, 12 is 16 also divisible by 4. So their summation is a multiple of 4. So how many order pairs? 1, 2, 3, 4. So there is total 4 order pairs under the definition of R2. Then let us see the next problem. That is R3 will be what? R3 will be what? R3 is given as number 3. R3 equal to within first bracket A comma B such that for A less than 10 comma A minus B belongs to N. It should be a natural number. Where small a belongs to capital A and small b belongs to capital B. Under this definition, what are the order pairs? Let us see. So the given two sets are already given above. So from there, according to the definition, by the definition of the relation for R3, what will be the order pairs? Let us see. So first of all, A should be strictly less than 10. A should be strictly less than 10. So in case of A less than 10, there is no any elements. So definitely since there is no any element for A less than 10, therefore it will be 5. The relation R3 will be 5. Because there is no any element less than 10 for small a. That is why this relation will be 5. Means null relation. Some special types of relations. First of all, say A equal to A, B, C. Then A cross A will be within second bracket A, B, C. Then A cross A will be what? A, B, C. Then cross product, Cartesian product of these will be A comma A, A comma B, A comma C, then B comma A, B comma A, B comma B, B comma A, B comma B, B comma C, B comma C, next C comma A, C comma B, C comma B, then last one C comma C. So how many order pair? 1, 2, 3, 4, 5, 6, 7, 8, 9. Total number of order pair will be 9 here. So if A equal to ABC, then A cross A equal to AA, AB, AC, BA, BB, BC, CA, CB, CC. So total number of elements here given 9. So what is called identity relation from here? Identity relation under the set A will be AA, then B comma B, then C comma C. So this is called IA, means identity relation on A. AA, BB, CC. This is called identity relation on A. Means relation will be from A to A. Then what is called reflexive relation. If I is the reflexive element, then it will be say AA, comma BB, comma CC, and A, comma B also we can write here. So including all the identity elements, along with that, if we include any order pair, then definitely it will be reflexive. This is called a reflexive relation. Reflexive relation. This one is called identity relation. Identity relation. So identity relation is like pattern A, B, B, C, C. But for all elements it should satisfy, then it will be identity relation. So reflexive is little different. That is, each and every identity relation is a reflexive, but each and every reflexive relation may not be identity. If there is any extra element, then it cannot be identity. So it is a reflexive but not identity relation. Let us see what is called symmetric relation. Besides these two, what is called symmetric relation? Symmetric relation. If another relation symmetric relation. What is called symmetric relation? Say another relation from A to A such that A, comma B and B, comma C. Say another element C, comma B, AB, BC, CP and BA. Here for each and every order pair there should be its inverse order pairs also supposed to have, then it will be a symmetric relation. For each and every element of A, it is not necessary, but whatever order pair is given, so its reciprocal also must present in that relation, then only it will be symmetric. So this is one example of a symmetric relation. So let us do one more, what is called transitive relation. What is called transitive relation? That before the transitive relation, if we want to explain about the antisymmetric, if a relation is not symmetric, then it will be antisymmetric relation. If a relation is not symmetric, then it is called antisymmetric relation. So what is called about the transitive relation? Let us see. The pattern of transitive relation is what? If another relation such that A comma B, B comma C and A comma C. If in any relation A comma B, B comma C implies A comma C also must present here, then it will be a transitive relation. Transitive. transitive relation. So what is called transitive relation? If A comma B and B comma C belongs to a relation, and at that moment there should be another third relation is A comma C, then we can say it will be a transitive relation. If in a relation there is only one order pair, that is say A comma B only, there is no more order pair. So each and every single order relations is a transitive relation. That was supposed to remember, all of you. Each and every single order relations, each and every single order relation is a transitive relation, because there is no more order pair to compare. That is why each and every single order relation is a transitive relation. So what is the equivalence relation? If a relation can satisfy, say, it should be reflexive, symmetric and transitive. If a relation can satisfy, that is reflexivity, symmetry and transitivity, then particular relation is called equivalence relation. So here A cross A is also, we can say, the one universal relation which is an equivalence relation, because it will satisfy all the three types like reflexive, symmetric and transitive. So that is why it is called a equivalence relation. So let us see some more problems about reflexive, symmetric and transitive. So about this, in the detailed explanation, I'll discuss in the next class. Thank you for today.